Before we get started on tonight's webinar, I would just like to announce next month's webinar, which will be November 27th, and it's with the Beyond Center's own Louis Slocum, and his topic is Life Quantum? And then for tonight's webinar, if you joined us before, it's the same format, but if you're new, if you have any questions during the presentation, you can just submit them using the Q&A feature at the bottom of your screen, and then we'll get to those towards the end of the hour. So with that, I will go ahead and turn it over to the moderator for tonight's talk, Maulik.
Hello, everyone, and welcome to this evening's latest episode of our Thinking Beyond series. So you all know the format, I hope. Many of you are regulars, I think. So there's a chat. Just enter your questions throughout as we go along, and at the end we'll have a Q&A. So about 50 years ago or so, the work of Jacob Bekenstein and Stephen Hawking um, showed that when the laws of quantum mechanics are applied to black holes, they are even more amazing than we thought. And so the black holes, which had already been sort of the coolest and some of the most intriguing objects in the universe, became, as it was later understood, the key to understanding the ultimate quantum nature of space and time. And that investigation has been going on for about 50 years. And at the forefront of that effort is our very own Professor Cynthia Keeler. Cindy is the associate professor in the Department of Physics here at Arizona State. And her brief bio is that she did her PhD at Berkeley, followed by postdoctoral positions at Harvard, Michigan, and Niels Bohr Institute in Copenhagen. And she's now on the faculty at ASU. And without any further ado, here she is.
All right, thank you, Maulik, for that nice introduction. I'm going to go ahead and share my screen. Hopefully everybody can see my slides okay here. And I wanted to go ahead and start off, first of all, just by a very brief aside, stating why I'm going to be using this bright gold color throughout. And that's because, as you probably know, the ASU colors are, of course, maroon and gold. My background has the lovely maroon color, and the gold will also be showing up throughout. So what we're going to talk about today, I want to start, first of all, by talking a little bit about the general relativity background, and then we'll get into how we're going to augment that with the quantum nature of spacetime. First, I want to start with the nature of spacetime, just on a classical level, what we have originally. So the Einstein equation tells us that the curvature of space is related to the energy or the matter in that space. As we put in more energy, the space gets more curved. So the moon, satellites, me when I pull off the bouldering wall, light all follow this curvature. But what happens if we try to stuff so much matter and energy together that not even light can get out? Of course, this is when we get a black hole. So what are black holes? They're a place where they have an event horizon. Gravity's so strong that light can't escape. It can't get out to those of us on the outside. Famously, they have no hair. So the only things that you can know about a black hole from the outside is its charge, its mass, and its spin. And whenever you throw anything in, the area of the black hole just gets bigger. It'll settle back down, still be a black hole, but the area of that black hole will be bigger. So they're a great lab for theorists, but importantly, they're also actually real. At the center of our galaxies, we've been able to provide images of them. So this is from the Event Horizon Telescope here. I think this one might be not at the center of our galaxy. I think this one might be M87, but I'm not sure. But this is a really recent collaboration. It takes images from a bunch of different telescopes and puts them together and is able to image very close to the black hole. So they're a few radii away from the black hole, but really quite close to it. We've known about ones that are closer to the size scale of a single star, like the solar mass scale, for a while, because we can see them due to the accretion disk, the matter that's spinning and coming into them. That matter sends off light. We can see that light, so we know that they have to be there. And then, of course, about 10 years ago, the first observation of black holes colliding with each other and sending out gravitational waves, we were able to observe those gravitational waves via the LIGO Observatory at Hanford and Livingston. And I want to say a little bit about this curve. So here, this is sort of the gentle region where the black holes are spiraling in towards each other. It's called the in-spiral. And then out here is after they've merged and they're kind of ringing down and becoming just a plain old black hole again. And in the middle here is a numerical mess. It's a very difficult to model region of intense gravity. So this is one of the things that we might want to be able to explain and understand well from a theoretical perspective, because it's something that we can measure now, but it's very hard to give exact details about what analytically what goes on there. So let me say a little bit more about this concept that anything you throw in, the area just gets bigger. It doesn't matter what I throw in. I throw a cactus in, I throw the sun in. If there's a wildfire nearby and I take all that smoke and I throw it in, no matter what I throw in, all of the things that I throw in are just going to make the black hole a little bit bigger. So my black hole, in the end, it's a little bigger. And even if I throw in a whole other black hole, so this is actually from a numerical simulation from NASA Goddard of throwing one black hole into another, but the same thing happens at the end and verified by LIGO data. We still just know the mass, the charge, and the spin. That's all we can see from outside the black hole. So where did the information about that cactus we threw in, or the sun that we threw in, or even the other black hole, where did that information go? Does the black hole know what it is? And does it have any plans to tell us if it does know? To examine further, I want to take a look at another quantity that always increases in any physical system. This is the entropy. So entropy is the name given to one of the quantitative elements which determine the thermodynamic condition of a portion of matter. At least that's what the Oxford English Dictionary says if I look it up. I'm not sure how much intuition this gives us, but it is technically correct. Another possible definition one could use, it's the tendency of systems to settle into their most common state. It's a measure of disorder. Wikipedia tells us that it's a measure of the amount of thermal energy that cannot be used to do work. And of course, it's 2025, so I had to ask ChatGPT, and ChatGPT tells us that entropy is a measure of disorder, randomness, or uncertainty in a system, reflecting how spread out or unpredictable its components or information are. All of these definitions kind of have the right set of words and the right set of feelings around them, but I don't think any of them are really quite a precise definition of entropy. So I want to give you one formula. I promise this is the only formula I'm going to use in the talk, but I want to give you this one formula. And that's that we're going to call the entropy the logarithm of the number of accessible microstates. So I want to talk about the pieces of what's in this equation. The first piece is the log. Logarithm is useful just for discussing large numbers. It's going to give us the exponent. And an accessible microstate is a particular microscopic arrangement whose properties match your requirements. So consider, for example, the room you're sitting in. It's probably about a 10-meter cube, roughly, more or less. And let's say that there were 100 molecules in that cube. Obviously, there's a lot more molecules than that in your room, I hope. Otherwise, you're probably not breathing very well. But let's take those 100 molecules and say, okay, what if I force them to actually hang out in just 1 meter cubed in one little corner of your room? How many different ways are there to arrange them, insisting that they stay in that cube? Well, it turns out I'm going to model each one of your molecules as just a 1 angstrom cube itself. And then how can I put 100 of those little cubes somewhere in the 1 meter cube corner of your room? Well, there's about 10 to the 330 ways, different ways I could arrange those molecules. That's quite a lot of ways. But if I let the molecules spread out through your entire room, so they're not stuck in this little corner, but now they can move out through everywhere in the whole room, then I get 10 to the 3,300 ways to arrange them. So there's a lot more ways that I can arrange the molecules in the full room versus in the little tiny space that's just this corner here. How many more ways? Well, I wanted to write out the number of zeros that are involved here, and please pardon me, this takes a couple pages. So here's the first one. This is the second one. And then this is the third one. So you can see why we use exponents for this, because it's 10 to the 2,970 more ways. That's a lot more ways. It's a really big number. If I pick one configuration of molecules in the full big 10-meter cubed box for every yottosecond, that is every 10 to the minus 24 seconds, it will take 10 to the 2,028 times the lifetime of the universe before we even have half a chance of hitting a configuration where all the molecules hang out in that one small corner of your room. So pretty much it's not going to happen. There just isn't enough time. And one of the things that entropy tells us is that we're going to go into a configuration that's much more common. So we're going to go into the configuration where the molecules are spread out throughout the whole room. It's convenient because it helps us breathe, because the air is actually everywhere in the room, but it's also mathematically just a much more probable case. If we're randomly picking distributions, we're going to get one where the air is spread out throughout the entire room. Okay, so this is a technical definition of entropy, but I wanted to check and see if our audience today has any intuition about entropy. So I'm going to start us with a picture here where what I've done is I have a beaker and I've dropped some dye in the beaker, and we're going to see what happens as I move forward in time. So as I move forward in time, the dye is going to contract together and take up less and less space. It'll become denser and denser until finally it's just a little drop on the top. Now, unfortunately, because of the nature of this presentation, I can't actually see if any of you were surprised by this, but I expect some of you are, because of course something's not right here. What I've been showing you is a sequence of pictures in the wrong order. We want to go forwards in time. We know from experience that what happens when I drop dye into a beaker is that that dye is going to spread out. And eventually, if I wait long enough, it'll be evenly spread throughout the beaker, and the whole beaker will be the same sort of light pink color from this red dye. So this is the thing that we actually expect to happen. This is the direction that time goes. Time goes in the direction where entropy increases as we move forwards. This is the second law of thermodynamics, that in any process, entropy is always going to move forwards. I do want to spend a minute going through all the laws of thermodynamics, and then we'll talk about how they apply to the system we care about, which is the system of black holes. So I have to apologize. The laws of thermodynamics turn out to be a game that's not very fun to play, but I'm going to describe the rules to you anyhow. The first rule, or the first law of thermodynamics, can be stated as you can't win. That is, to do any work, you've got to put in some energy. How much energy? The temperature times the change in entropy. The second law is the one we've already talked about. You can state that as you can't break even. No matter what you do, the entropy in any process is going to increase. For the third law, well, you also can't quit the game. So except if you could get to absolute zero, but you can't get there, so you can't quit. And there's one more law that people sometimes state called the zeroth law, which can be stated as you have to play the game. And this is because thermal equilibrium is going to happen whether you like it or not. So I apologize for the unfortunate game that we are all forced to play. But I want to point out that it really highlights how important entropy is in our world, because it's really telling us what happens in any process. It's going to increase, and it's telling us exactly how much energy you have to put in order to get useful work back out. I also wanted to comment that entropy is a concept that's useful outside of theoretical physics. So today I've been talking to you mostly about how it's useful for theoretical physics, but it's a really useful concept for studying information theory, which tells you about how signals get sent to your cell phone and back, how much information you can pack in the bandwidth of your cell phone signal. You can do a calculation that's based on entropy to find that. You can analyze the way that stocks are going to behave by the entropic behavior of the noise in the system. It's shown up in literature, famously in Tom Stoppard's Arcadia, and it actually shows up in things like linguistics as well. So languages change over time. They accrue small differences and small changes, and you can model this as the entropy of that system increasing too. So it gets used in really broad ways. Of course, today I'm mostly interested in how it gets used for black holes, because that's what I want to talk about. So In the regular thermodynamics, we've seen that entropy always increases. The dye is going to spread out, the air molecules are going to spread out and be throughout your entire room. Well, we also saw in black holes that no matter what I threw in, whether I threw in a cactus or the sun or another black hole, the area of that black hole had to increase. So we can write the generalized second law of thermodynamics as all processes are going to increase the sum of the entropy of all the matter in the universe and the surface area of all the black holes in the universe. So this sum always has to go up no matter what we do. Also, famously, as Maulik alluded to in the introduction, black holes do have a temperature. They have surface gravity. So surface gravity you can think of as, imagine that you had an astronaut who was willing to go and hang out at the edge of a black hole. So you're going to connect that astronaut to a long tether that goes very far away. And then how hard do you have to hold on to that tether to make sure that the astronaut doesn't fall in the black hole? That tells you what the surface gravity is of the black hole. And it turns out the surface gravity is related to the temperature at which they send out Hawking radiation. This temperature is really tiny. So for a solar mass black hole, for a million solar mass black hole, like the one at the center of our galaxy, the temperature is about 10 to the minus 13 Kelvin. For context here, the cosmic microwave background radiation is a few Kelvin. And the temperature in your room right now is probably about 300 Kelvin. So 10 to the minus 13 Kelvin is very, very cold. It's a very, very small temperature. But on the other hand, the entropy of these black holes is very large. If I just calculate what the area is and I turn that into entropy, it turns out there's more entropy in the single black hole at the center of our galaxy than in all the matter in the entire visible universe. And remember, most galaxies seem to have black holes at the center of them. So the amount of entropy from all of these black holes in all of these galaxies all over the universe is much, much larger than the entropy from all of the matter. A black hole, in fact, can actually be thought of as the most entropy that you could put into a given region. If you tried to put more entropy in there, you'd just make a bigger black hole. So let's go back to our laws of thermodynamics and see if we can write down the same things for black holes instead. The game isn't going to get any better. We still can't win, but this time what we can't win means that the surface gravity times the change in the area of the event horizon will be the change in mass. That we can't break even is this concept that the area just gets bigger no matter what we try to do. And we can also state that we can't quit the game. And of course, you have to play the game. Hawking radiation is going to happen. Your black hole is going to reach the thermal equilibrium with the world around it. So we're learning here that entropy is important for understanding spacetime because it's deeply related to what happens with black holes. So let's go back and think about our cactus, this friendly cactus that we threw into the black hole. The black hole got bigger, but from the outside, we can't see what kind of cactus it was anymore. You don't know if I threw in saguaro or an ocotillo or what I threw in. You don't know how big it was or how many spines it had. All you know is the mass of what I threw in because the black hole got bigger according to the mass of what I threw in. So this loss of information or apparent loss of information is known as the Hawking paradox. And we have quite a lot of proposed solutions to the Hawking paradox. And I'm going to tell you a little bit about a couple of them. So the first possible solution is the idea of remnants. So if I have a black hole and I've thrown some stuff into it, but from the outside, all I can see is the mass, the charge, and the spin. Well, as the black hole is radiating energy away when it's Hawking radiating, it's going to start to shrink. It's going to start to get smaller. So it seems like the entropy in that black hole, because the area is going down, should be going down. Where did the information of the cactus that I threw in end up going? If the black hole shrinks all the way to zero size, then the information seems to have totally disappeared. It's not in our universe anymore and we can't access it. Well, a remnant is saying as the black hole shrinks, once it gets to some size, it actually stops shrinking, and now it acts like a quantum object. It's not going to shrink anymore, and the information is just stuck inside of it. And maybe it's very hard to get out, but it hasn't disappeared from our universe. It's just stuck in some very tiny, tight ball. Another possibility is the idea of complementarity. So complementarity basically says, when we throw the cactus in, it looks like we've lost the information, but actually Hawking radiation is more detailed than we thought. And somewhere as the Hawking radiation is coming out, it's telling us, hey, there was a cactus in here. You threw a cactus in. So maybe there's copies of the information, one that fell into the black hole and one that gets shoved out with the Hawking radiation as it comes out towards us. Another possibility is the idea of fuzzballs. So in a fuzzball, this is a statement that a black hole isn't as boring as I told you. So I told you from the outside, all we know is the mass, the charge, and the spin. But what if that's just an approximation? If we could look closer and see in more detail, maybe we see that the black hole just approximately looks like it has only mass, charge, and spin. And actually, it's some complicated, say, object coming from string theory that has a lot more details to it, and those details are carrying the extra information. It's called a fuzzball because you might think of this as like a giant wad of spaghetti that's about the size of your black hole and looks very much like a black hole when you probe it from the outside, but if you get close enough, you'd see it's actually a giant ball of spaghetti. Another possibility is a set of ideas that come out of quantum information. And they have to do with you can mathematically restate this Hawking paradox, asking the question of where the answer went, where the information went. But in order to actually test where the information went, say you want to shove one of your friendly astronauts in the black hole, and the other is going to stay outside for a while and then jump into the black hole later. When those two meet up, they have to do a calculation to see if they agree about where the information was. Well, that calculation takes time, and there are some quantum information limits on how long that time is going to be. And it turns out they don't really have long enough. They hit the singularity before they would have time to do the comparison. So maybe there's no good way to formulate the question precisely with people who can actually compare their answers because there are quantum information limits on how we can do that. And the last possibility that I wanted to mention is one that's been quite popular in the last 5 to 7 years, which is called islands. And this is an idea that explaining the quantum gravity of the situation will allow us to see large changes in how we calculate the entropy of the black hole when we include quantum effects in certain regimes. And these large changes are particularly important for what are called large old black holes. These are black holes that have been around for a while and have already sent off a bunch of their Hawking information. Hawking radiation, that means they've already sent off a bunch of their information. So they're the ones where the tension of this Hawking paradox look most strong. And in these islands, they're able to actually use them to describe how the entropy of the black hole starts to go back down when you include the effect of the Hawking radiation and the universe around it. So you need to include not just the Hawking radiation, but all of the things that it's going to talk to in the universe. We might call this we use the term bath to describe large thermal object you're interacting with. When you include that bath, you actually are able to recover that the information seems to be doing something reasonable. So the main point I want to make today is we have a lot of possible solutions. We're not really sure which one is going to be the correct solution. None of these is a complete, full answer to it. And importantly, we don't even know if the black hole itself actually remembers how it was made. And if it does remember, we don't know if it has any plans to actually tell us. So let me close by giving a quick word from our sponsors. So I showed you some lovely pictures today. One was from LIGO, that's funded by the National Science Foundation. The Event Horizon Telescope, also funded by the National Science Foundation. This Goddard series of numerical simulations was funded by NASA, and I am funded by the Department of Energy Office of Science. So I just wanted to point out how important American national funding is to try to produce this science that we all want to understand better so that we can understand what the actual fabric of our universe is made from. Okay, so that's all that I have for you guys today.
Great. Well, thank you so much, Cindy. So if the audience has questions, as I'm sure you do, please enter them into, I think, is it the chat or the Q&A? I'm a little bit unclear about that. Jessica, do you know where they're supposed to type them
Yeah,
in?
it's in the Q&A.
In the Q&A, right. I'll start with some questions that have already been asked. Um, so, um, so you use the term area to describe the entropy of a black hole, and so and you've also mentioned that area has something to do with the information in a black hole. So it seems to me, or it's that the total amount of air information you could put inside a black hole depends on the surface area and not on the volume, right? Normally, the amount of stuff you can cram into a bag depends on the volume of the bag, not the surface of the bag. So can you tell us a bit more about what that means and why that's so profound and what have we learned from that?
Thanks, Maulik. That's a great question. So, first of all, just to say a little bit more about the question, the first example I gave you about the entropy in a room with how all the different ways that I can arrange the molecules, that actually does scale as the size of the volume of the room. So, if I make the volume of the room twice as big, then the entropy would be twice as big. Note that if you make the volume of a room twice as big, you don't usually make its surface area twice as big. Now, the surface area will get big less fast than the volume does. So there's a question about why black holes don't seem to behave that way, because it looks like their entropy depends on the surface area instead of depending on the volume. Uh, and I can say two things about this. So, first of all, that's just what comes out when you build what the equations are for how black holes evolve in time when you add matter to them. What you find is the thing that's constant is the area. So we have, just from the equations of general relativity, we have some evidence that the area should be the thing that's constant. And then from Hawking's calculation, we learn that that area really can be interpreted as an entropy. But what does this tell us about the weirdness of space-time near black holes? What's strange about this? Well, as we mentioned, it's already strange that the entropy seems to scale like this surface area rather than scaling like the volume. But we think that this might be tied to an idea from quantum gravity that's called holography. And this is the notion that there may be a map between the space-time we live in 3+1 dimensions, and some theory that lives on a boundary surface of this space-time. So that would be something that's just 2+1 dimensions. You can think of it as like a large sphere enclosing everything that we live in. And maybe all of the data that describes us can actually just be written on the surface. Certainly, this is what we see for a black hole. All of the data that describes the black hole apparently can be built from just its surface. You might imagine this as a bunch of little squares on the surface, take little things the same size as the Planck scale. So the Planck scale is the scale that we expect quantum gravity to be at. This is 10 to the minus 35 meters about. Take a bunch of little squares on the surface of the black hole and write a 0 or a 1 in every one of those squares, and that'll get you the same amount of entropy as the same amount of information as the entropy mapping to the area indicated you should have in the black hole. But that means if I want to describe what's going on inside the black hole, evidently I only need to tell you what's going on the surface area of that horizon. I don't need to give you more information in order to build up the whole thing. And you would need something like holography in the context of quantum gravity for that to be true.
Great. So I have a related question. This one is from our very own Barbara Temple, who always attends these, but unfortunately couldn't come today. She sent this question by email, and it says that, well, so it follows up on what you were just saying, that in a sense, if the information is on the surface, in a sense, one dimension, the interior dimension is sort of redundant almost. It's almost as if we don't really need that to describe what's going on there. And so taking this further, not just for black holes, but there's this there's an idea that the entire universe might be like this, that there's an extra dimension that we're really kind of a projection of a hologram, as it were. Can you tell us a bit about that? You were already
Yes,
talking about that, but do you?
yes.
Yeah.
It's highly related to what I was just talking about. Thank you, Barbara, for bringing this up. So, in this idea of holography, uh, indeed, we think that our entire universe that we live in is built up from a sort of hologram where I can describe all the physics on a surface that's one dimension down, and then that tells me about what's happening in the 3+1 dimensions I live on. But that doesn't mean that we don't need the 3+1 dimensions that we live in to give us a nice description of what happens, say, in our daily lives when we're not jumping into or trying to jump out of black holes. Uh, the 3 plus 1,
Sorry, just to jump in here for the
yes,
audience, when she
please.
says 3+1, it's not because she can't add them to 4, but because 3 is space and 1 is time. That's how physicists describe space-time.
I am also a pure theorist, so 3+1 is getting into pretty big numbers for me. So, in my defense, yes, Maulik is correct. I'm referring to the fact that time is a bit special. So I'm going to call 3 space, 1 time, 3+1. Uh, so right. So if I want to describe that 3+1 dimensional space, maybe I can, in fact, rewrite it in some complicated way, just as a bunch of data that's living on some 2+1 dimensional surface. So this is a surface that has 1 time dimension and 2 spatial dimensions, but nothing else. But it might be more complicated for certain things. In fact, the duality that we think exists, so this is a duality that describes this full bulk space-time of 3+1 dimensions in terms of a 2+1 dimensional surface. It's what we call a strong-weak duality. So we want things to be weakly coupled if we want to give them a good description. What do I mean by this? I mean, we don't want everything around us to be uh, really non-linearly talking to everything else around us. It's too complicated and hard to describe. We're good at describing things when we can expand them in terms of a basic setup and then small little changes to that setup that aren't very strong. When those changes start to get really strong, we have a hard time discussing it. This mapping between a strong and a weak theory means that when the gravity itself in the full 3+1 dimensions is a really good description, that means that the description on the other side in this 2+1 dimensional hologram is really complicated and hard to understand. But the same thing is true the other way around. So when that 2+1 dimensional description is really simple, it means it's describing something that to us looks really complicated. So cases like colliding black holes or like asking questions about the information paradox, sometimes it's really useful to map it through this duality and look at it in the case where the description might be a little bit simpler. So it's really a question of both things describe our physics, which one's easier? And you should pick whichever one's easier for the kind of physics you want to think of.
Okay, so that's already quite shocking that the information of a black hole, it's almost like all the information in a book is only written on its cover, if you like. But the other strange thing about black holes is that they have temperature, right? Because as Stephen Hawking showed. So normally if something has temperature, if it's hot, then you feel its warmth, it's radiating. But the whole defining feature of black holes is that nothing can ever get out. So how is this radiation coming out? Can you tell us a bit about the essence of Hawking radiation?
Sure, I can tell
That's
you a
one of the
little bit about
questions.
that. Yeah, let me see if I can slide back to our map between the equations of thermodynamics, or the rules of thermodynamics, and the rules of playing with black holes. So these rules are built for what's called semi-classical gravity. This is when we are doing gravity and adding just a little bit of quantum mechanics in. So we can think of this as the black hole is just there, it's not changing in any way. And then I'm going to ask what happens if I, say, create an electron and positron very close to the event horizon of that black hole. And we ask, well, where do those go in the future? Maybe one of them falls in and one of them goes out. And one way that you might imagine you could see Hawking radiation is by seeing this stream of little particles that are pair produced near the edge of the black hole horizon. By the way, this is something that's actually happening around us all the time. You may have heard the idea of vacuum energy before. And in quantum field theory, we think vacuum energy is happening because there are all these little pairs of particles and their antiparticles that get produced and then they annihilate. They get produced and then they annihilate. They get produced and then they annihilate. Quantum mechanics allows us to violate the conservation of energy on really short timescales. So very briefly, I could get away with making a pair and then letting it go away. But if this is happening everywhere throughout our space-time, it's going to do some weird things when it's happening right at the edge of a black hole. So one could escape and one could fall in. And this might be a way of thinking about what's happening with Hawking radiation. It's happening due to quantum mechanics occurring very close to the edge of the horizon. So I'm not sure how much that addressed your question, Maulik. If you have follow-ups, I'm happy
Yeah.
to talk about that.
I think I'm going to switch to a different question that was asked. This is
Mhm.
uh, about just you mentioned something called the no-hair theorem, and maybe you can elaborate on that. In particular, Joseph Wigginton is asking if a black hole is such a simple object described by just one or two parameters, right? These are the hairs of the black hole, the
Right.
mass, the charge, and the spin. Why is the entropy so high? It seems like it would be very low.
That's a great and perfect question, and this was very baffling to physicists for a really long time. Basically, ever since Hawking's calculation in 1978 that black holes should radiate and with an entropy that appears to be so large, uh, ever since then, I think people have been wondering about the answer to this. So essentially, it has to be that there are large changes to what you see in classical gravity. Classical gravity just by itself can't possibly explain to you how the entropy is so large when there's just these three pieces of data you have. You need a lot more data to get large energy or large entropy, sorry. And actually, one of the solutions that I'm a little partial to myself is this fuzzball solution, exactly because it allows you to say, hey, from the outside, it looks like there's only these three numbers. But in reality, when we get close to it, it's not perfectly spherical anymore. It's some highly quantum, maybe a string theory kind of object that has a lot of complicated features, and there's a whole bunch of different ways I can arrange those complicated features. Um, I should also say one of the things that brought string theory some press in its early days back in the 1990s, so back when I was a high school student, was a calculation by Andy Strominger and Kumru Vatha, where they took some really special black holes that were highly symmetric, not like the ones in our universe, but ones that obey a thing called supersymmetry. And they actually calculated, hey, how are there are bits and pieces that make these black holes up? They still look macroscopically like they just have a charge, a spin, and an angular momentum, but there's a lot of different ways I could have built the building blocks of them to make them look the same for their charge, mass, and angular momentum. How many different ways can I build those building blocks? And they got the right number. The number of accessible microstates matched up perfectly with what they expected for the entropy of the black hole. And I should say, sort of this fuzzball program grew out of that original calculation, they were trying to make it something that might be more realistic for the black holes in our actual universe, which are really different from the ones that were being worked on in the 90s. But that's a great question. It's exactly, we'd love to know.
Okay, so yeah, so basically you're saying that this black holes could be just this idealized objects that we think have only three parameters, in which case their super high entropy is baffling. But then, as your postdoctoral advisor showed at Harvard, that there is a way to precisely enumerate that entropy by using string theory.
And we've
Right.
done it successfully in a few specific cases. I don't think it's really been done successfully for the black holes that are in our universe yet. It's something people are working on.
Right. So this is somewhat related to that an anonymous question. Since mathematics allows us to imagine more than three-dimensional space, how does that affect our understanding of a black hole? So of course, this is what Strominger did.
Yes.
You want to say a bit more
Well,
about it?
yeah, among other simplifications, they were I actually can't remember. That is that a set of five-dimensional black holes that they were
Yeah,
working with?
four plus one. Right.
4+1, yes, because
Yes.
that's how we do things.
Yeah.
Yes, that's right. So
For technical reasons, it was easier to do the calculation in five space-time dimensions rather than four.
yeah.
Yeah.
So
Okay,
mathematically,
sorry.
I was just going to say mathematically, we can imagine writing down black holes in all sorts of dimensions, and we do this a lot to make things calculationally easier. And then we hope that what we learn in some other dimensions is still kind of like what happens in four. So most of the work on this islands paradigm is actually done in the case of just 1+1 dimensions. And yeah, there are people who are working pretty hard to try to bring it to four, just like these fuzzball people are trying to take the 4+1 and bring it back down to 3+1 so that it matches our actual universe.
Right. So here's a question from Howard Lannis, who says, since we can store information inside a black hole, could we use them as archives?
Uh, if we knew
And
how to get the information back out, the other problem with black holes is that we don't know how to create them other than on an astrophysical scale. So we know how black holes are formed when a supernova happens or a neutron star collapses. And we also know a bit about how they form over much longer timescales when a galaxy comes together. And you get a supermassive black hole at the beginning. But we don't really know much about how to create ones that would be small enough to, say, carry around in your pocket. The other problem is that the temperature of the black hole actually goes down when it gets big. The bigger it is, the lower its temperature. So I gave you some number 10 to the minus 14 Kelvin or something for the temperature of a galaxy scale million solar mass black hole. But if I want to make one that's small enough that I could carry it around, that temperature is going to get pretty high. The other problem is that they're quite dense, and things that are that dense don't tend to play well with the things around them. So I think as far as a practical storage mechanism that you could move around, it's probably not our best bet.
I just want to follow up on what you said. So black holes, we typically think of them in the popular imagination as being these astrophysical objects that are, really dense and, somehow related to astrophysical things, which are really big. But the laws of Einstein's theory don't require the black holes to have any particular size. And you could have really tiny black holes, right? You could have microscopic black holes. In fact, there was a concern in this accelerator in Geneva, that in the Large Hadron Collider, that we might inadvertently create black holes by smashing particles together. So, so black holes can come of all sizes, and in particular, they could even be primordial black holes, right? So could they be dark matter?
Yeah, that's a great question. So I should say, first of all, I'm not an expert on the current limitations on using black holes as part of the dark matter. But yes, this is something people take very seriously and try to study. In particular, Maulik mentioned this idea of primordial black holes. So these are black holes that are formed very early after the birth of the universe, after the Big Bang. And that we're saying primordial because they've been around for a long, long time. And indeed, it is possible that they could be some component of the dark matter, maybe not all of it. I think there are limitations on that, but they could be some component of it. I think, am I correct that Roger's postdoc Kevin it works on this? I think we have a couple of people at ASU that
Yeah.
focus on this.
Right. So it's pretty clear. I think it's pretty clear that they're not all of the dark matter, but they're not ruled out as potentially a significant fraction of it still.
Yeah, they could be up to a third or so of it, I think.
Right, right. So dark matter doesn't have to be one thing. It could be a combination of different things that we can't see. And one of those could be black holes. So a related question that's cosmological is that Derek Youngson asked, you mentioned there's more entropy in all the black holes in the universe versus the entropy of all the visible matter. And what does it say about the total energy in black holes versus visible matter?
That's a great question. I actually haven't done that calculation. I don't think it tells us very much because I think that energy in the black holes scales like its mass, so it scales like what the size of the radius, say, of the black hole is. And I think that that still ends up being not a terribly significant portion.
Right.
Um, Partially what this is telling you is that the entropy in these black holes is really, really high. So this conflict between, hey, they're supposed to have no hair, just these three numbers, mass, charge, and spin, versus what the entropy says the amount of information they should have, that conflict is very, very big.
Um, so let's see. Okay. So can you say a little bit about the way that black holes distort time and how time might be distorted within the black hole? Um, yeah, you didn't really touch on this, but this is, of course, another fascinating aspect of black holes.
Yeah, let me think about that for a second.
That's
So
a question from Hunter Riley.
it's a good question. Let me first of all talk about how they distort time for things traveling past them. Um, so there's a thing called the Shapiro time delay, which is an effect. It doesn't happen just with black holes, it's just bigger with black holes. Happens with, say, when you go past the Earth, too. So if you're a tiny little particle and you're traveling past the Earth, general relativity tells me that because you get a little bit curved by the path of the Earth, rather than traveling a straight line, say you're traveling a straight line between this point and this point over here, you'd be able to travel that straight line faster if there weren't this mass. The mass makes you travel a curved path, and the curved path is a little bit longer than the straight path would have been. So it takes you a tiny little bit of extra time to get past it. Well, if you're going very close to a black hole, that tiny bit of extra time gets bigger. Uh, how much bigger depends on how close you're getting to the black hole and how fast you're traveling and when you go past it and so on. Um, but even for those of us who stay outside black holes, the extremity of their gravity affects the way that our clocks behave. Now, when you jump in a black hole, I want to discuss this from two different perspectives. One perspective is I'm not jumping in the black hole because I don't do that. You jump in. I watch you as you jump in. And imagine you're sending me a little burst of light as you fall in. Let's say you have a very precise clock, and so you're sending one burst of light at me every millisecond. What I'm going to see as I watch you fall in and I watch you get closer and closer to the event horizon is that the rate of those bursts of light that I receive slows down. In fact, it eventually becomes infinite as you get closer and closer to the black hole. And when you get to the horizon, they're infinitely spread out in time. So I'd have to wait a very long time to see your last couple of bursts of light as you fall across the horizon.
So you're saying that a person outside could never actually sees anything ever fall into a black hole.
That's right, because they're just sending me light rays as they try to tell me, hey, I'm falling in, I'm falling in. But those last light rays get spread out and spread out and spread out, and I'll never see the very last one,
Right.
even
But
if I
they
waited
themselves,
the
but
entire
that's an
time.
optical illusion because they're
That's
actually the person who fell
that's
in
right.
did fall in,
That's
right?
right. So from my perspective outside as the person who didn't jump in, I don't see them fall in. But if you jump in, and let's assume that you're not totally crazy, so let's have you jump into a very large black hole. A very large black hole may sound scarier, but it's actually less scarier because it's less curved. Uh, and so when you get to the edge of a very large black hole, space-time doesn't look that different to you. It actually looks kind of like it does now. You wouldn't necessarily even really know that you're crossing the horizon of a black hole. And so from your perspective, you just happily keep sending your blinks every millisecond and you go across the horizon of the black hole. And you wouldn't necessarily know right away. As far as we know, nothing dramatic happens. There actually was a theory, if any of you guys have heard it, called firewalls. That was another possible solution to the Hawking paradox, which is that actually something dramatic does happen and we just don't know about it. But I think most people think that drama right at the horizon is probably not very likely, although not impossible. So that
So,
means you just keep going.
so taking that literally, is it possible that we are actually inside a black hole right now? That maybe there's this massive, gigantic, entire universe could be inside a enormous black hole, and what we are going to call the big crunch singularity at the end might actually be the black hole singularity. Is that possible?
I don't think it's ruled out. If it's ruled out, if it's completely ruled out, I'm unaware of it. Note that the size scale that this would have to be is very, very big, because of things like we know that our universe is currently expanding and actually even accelerating that expansion. And so the size scale of any black hole we're stuck inside needs to be so big that there's room for the universe to accelerate within it.
Right.
So
But of
it
course,
does seem kind of unlikely.
there's no intrinsic size of a black hole. It can be
Exactly.
very big or very small.
So why
Right.
not make it extremely big? I don't think we've ruled that out. In fact, I'm not even sure I could come up with a way where you could
Well, I think
rule
it would be
out.
anisotropic. The space-time would be anisotropic, but of course, you know, maybe the different directions would not be quite the same
You know,
as they would as we observe in our universe. That would never actually rule it out
right.
because, yeah, but
Well, because you could
um,
have it's isotropic on our scale, but anisotropic on a much bigger scale.
right, exactly. Um, okay, so another question is if we could figure out how to get information out of a black hole. Well, okay, actually, maybe I'll ask the previous question. How would we decode the Hawking radiation? And could we
Uh,
work on that by maybe creating a tiny black hole at the LHC and using that to see how we can extract information from a black hole? Use them as kind of a very
it's tests.
tiny little hard drives where you can store an
Yeah.
enormous amount of data and then retrieve them through Hawking radiation.
Uh, so in principle, this is something you could imagine doing because if you think that the information is coming back out in the Hawking radiation, then if you can capture all of it, you might be able to decode it. But all of it, I really do mean all of it. So there's a calculation you can do with black holes that are ones that don't rotate. So uh, just they have a mass and nothing else. And you can do a calculation and ask how much of the Hawking radiation do you have to collect before you know just one bit, one of those zeros and ones on the surface of the horizon of the black hole. And it turns out you need about half of it before you know even one bit with reasonable probability. So the problem with this, of course, is that actually collecting all of the radiation would be very difficult. Even if you think about much less extreme objects like LHC, when you collide particles together at LHC, there's a sphere that encloses those particles, and we try to get all the data from it. But you can't get all the data because you have to have wires coming out some places, and because the particles had to come in somewhere, and so there's holes in what you're able to capture. You can't get everything. So because you'd have to have more than half of it before you get even one bit, uh, it seems still not the most practical of ways to get information back. Even if in principle it could be done, in practice it seems very challenging.
So what you're saying is that it's not like every particle that comes out of a black hole through Hawking radiation carries a bit of information that's, you can measure whether it's spinning this way or spinning that way or whatever. Instead, the information itself is encoded in a very subtle way through correlations between all these different particles. You would accumulate
That's right.
all of them to, in fact, that's very similar to the way that information is encoded in quantum computing, right? I think that
That's right.
so there's now been this great parallels between black holes and quantum computers. Can you, since that's something you've directly done research on, maybe you can tell us a bit about that.
I've done research on very much the theoretical end of that, but there are some actual, I don't want to call them experiments, I'll call them models that people have built, where they actually built an analog of a black hole in a quantum computer. So it's a little difficult to do these days because quantum computers can only handle a few qubits at a time. I think they were using something like 7 or 8 in the paper I'm thinking of. And what they did is they said, okay, we're going to take these qubits and we're going to put them in a state that kind of looks like a black hole, following our rules of how quantum information maps to black holes. And then we're going to watch what happens with it and see if we can get information to move in the way that we would expect. Um, and they performed a thing called quantum teleportation, where you use quantum mechanics to move information from one particle to another one that could be far away. And they were able to successfully do this, which is it's very neat. But because it's at this point, quantum computers can only do so few particles. It's really only an analog for a black hole. I don't think we could seriously call it a black hole in any way yet. But I will say that there are people who are seriously pursuing this and trying to say, okay, can we build a better model? Can we use rather than insisting that they be perfect qubits that are perfectly error corrected and controlled the whole way through, can we use near-term quantum computing techniques? So things that are kind of noisy and imperfect. Can we use those instead and still try to get something that looks like a black hole out? These are the kind of questions that people want to ask to see if this is a possible way forwards.
So in that, you're trying to model black holes with a quantum computer, right? Is that?
That's the idea, and
Yeah,
and
yeah,
not me specifically, but this is something that
I
the
know the paper you're
community
talking about.
has.
Yeah. But the other way around might also be possible. The black hole itself, if we could create and extract black hole information from Hawking radiation readily, then we could use black holes as quantum computers. We could create a black hole, start its state somewhere, and then I guess it wouldn't be very useful because we probably couldn't program it.
Yes.
It's just going to thermalize everything. Um,
Yes.
right.
Uh, I
Um,
don't think we'd have good. You want a couple things when you're building a quantum computer. So you want error correction, but you also want control. So you want to be able to set up a starting state and then control how it behaves in the future, like how it changes as you move on. And that second thing seems very difficult to do.
yeah, we could in principle control the state, but not the evolution,
Not its evolution.
not the
Yeah.
code itself. Yeah.
Yeah. Yeah.
Hmm.
Um,
That's
I
interesting.
will also say that on some level, you can, if you have fine enough control, you can build a quantum computer out of anything.
Right.
Because everything, if we think everything in the universe is quantum mechanical, then build it out of whatever you want. It's just a question of actually being practically useful for doing quantum measurements on. And that's why we tend to use these highly controlled quantum systems because they're not very noisy and we can precisely probe and control their action.
Right. But I guess the virtue of using black holes, if we, is that they could contain an absolutely staggering amount of information in very tiny space.
As long as we can figure out how to get it back out, sure.
Yeah, yeah, yeah. We're almost out of time, and you ended your presentation with a nod to our sponsor. So I'm going to end with a question that's about that. This is David in Abinet asks, and you don't have to answer this, but if you don't mind me asking, how did you get your start in this field and specifically with the Department of Energy?
Okay, so that's a great question. Um, the simple answer is that I was interested in physics from a pretty young age, and then I went to school for a lot of years and did preparatory postdocs at a bunch of places, and eventually managed to get a job here. And the Department of Energy Office of Science is one of two big groups, that and the National Science Foundation, that fund this sort of research regularly in the US, so it made sense to apply to them. But I think that's not actually the interesting answer to your question, so I'm going to give a different answer, which is about how I got interested in doing this sort of physics in the first place. And for me, it actually goes back to when I was in middle school, and my older sister was taking AP chemistry, and I would steal her book to read about it because it was cool and it had pretty pictures, and it had these beautiful pictures of atomic orbitals in it. And so I was reading what it said, and it said, any description beyond these pictures of what these orbitals mean is beyond the scope of this text. And it made me so mad because I wanted to understand where it actually came from. And in fact, in order to understand where it came from, I was in the middle of my undergraduate years before I actually understood the equations that describe the shape of those atomic orbitals. But this has driven me to try to understand, hey, where does this come from? That's been the question that's kind of been driving me since that age. And it's still what we're doing today. You know, we have, hey, here's a black hole. It's a thing I can write down. It's a thing we see in the sky and that we can measure. But where does it come from? What are its fundamental constituents? How does it act? What's beyond the scope of all of our tests right now? Um, and I think that's the real answer. That's not just about going to school for a long time.
It's always like that, right? It's always quantum mechanics that draws you in the end. Um, I
Well, I
think,
don't know. These days,
or
maybe it's
gravity, maybe.
gravity with I mean, I can't do a good mimic of the LIGO data here, but the little whoop sound that this makes, I promise you in 20 years there will be kids who heard that sound when they were young and decided it was really cool and wanted to go into it.
Yeah. I got into physics also because of quantum mechanics. But all right, well, we're out of time. Thank you all for attending, and thank you, Cindy, for this wonderful and stimulating talk. And see you next month.
Good night,
Bye,
everyone.
everyone.